Sometimes when we're solving a system of equations, we either just don't want to graph, or when we do graph, we can't clearly see the point of intersection. So there's something called algebraic solution methods, which means there are ways to solve the system and find out where two lines meet or if the two lines meet without actually having to make a graph at all. So the first method we're going to learn about is called substitution. The next method we'll learn about in lesson 3, it's called elimination. If you notice on the top of your note sheet, I've written you a list of steps with sort of key words to help you remember the steps. So substitution is one variable being replaced with an equivalent expression in order to solve the system. So this is another method we can use to find out where two lines meet. So step 1 is going to be to isolate one of the variables. Now, if we look at our very first example, notice y is already isolated. So step 1 has been done for us. And very often you will find that one or more of the variables has already been isolated, and that's why you're choosing to use substitution in the first place. Step 2 is to substitute. So we know that y is equal to 2x plus 1, because that's literally what this equation says. If I now go find the y in the other equation, I can substitute 2x plus 1 for the y in the second equation. So I'm going to start rewriting the second equation, and when the y pops up, I'm going to open a set of parentheses, and I'm going to write the expression that's equal to that variable. So instead of writing y, I'm writing 2x plus 1. Then step 3 is to solve this new single variable equation. Notice this equation looks longer than what we had before, but it's easier because it contains only x's. That's what we mean by a single variable equation. So we have 3x plus 4x plus 2. Always be careful to distribute when you go through those parentheses. We continue to solve the equation. We can combine our like terms and subtract 2 from each side, and then divide both sides by 7. And all of a sudden, we see why a method like substitution would exist. If I had drawn a graph and I got a point of intersection that had a coordinate of 3/7, I'd never be able to tell by looking at the graph that that's the exact value. I'd probably look at it and be like, I don't know, it's like close to a half. Like I wouldn't be sure, I could approximate, but this is going to let me find the exact value. Okay, now we know the value of one variable, but remember, we're looking for an entire point. So personally, I like to go ahead and sort of record what I've got already to remind myself that the y value is still missing and I need to find it. So the next section is to substitute again. So there's 2 layers of substitution. But this time what we're substituting is the value that we just found. We now know what x is. We know x is equal to 3/7. So it looks a little bit simpler to substitute it into this equation since y is already alone. So I'm going to say y equals 2 times 3/7. Notice anytime I substitute something in, I put it in parentheses when I let it replace the variable. Now I'm going to solve this part. I need to remember that multiplying a whole number by a fraction suggests that I should put the whole number over 1 so that I can multiply straight across. So I have 6/7 plus. Now 1 is equal to 7/7. So this is going to be equal to 13/7. So this is a really crazy intersection point that we never clearly would have identified if we had tried to solve by graphing. But solving with substitution, we get the correct answer right off the bat. All right, let's look at the second one. In the second one, going back to our steps, it says isolate one of the variables. Well, notice y is already isolated in both of the equations, so we don't have any work to do on that front. Step 2 says substitute. So if y is equal to 2x plus 7, then I can find the other y, and I can replace it with 2x plus 7. So I'm going to have 2x plus 7 equals x plus 6. I didn't use parentheses this time because the y was the only thing on that side of the equation, and therefore there's nothing for it to interact with. Now I can see I need to get all the x's on one side, so I'm going to subtract x from each side, and at the same time I could subtract 7 from each side. So I get x equals -1. If you chose to do that part, the solve, step 3, in 2 steps, that would have been fine. Okay, now we're ready for step 4, substitute again. We now know that the x value is -1. So we can substitute that either here or here. Well, the bottom equation looks a little less complicated, so let's go with that one. Instead of writing x, I'm going to write -1 because I now know that x is equal to -1. Well, -1 plus 6 is 5, so my point of intersection, the solution to this system, is the point -1, 5. In our third example, we're really going to need all 6 steps. Step 1 was isolate for one of the variables. And notice, none of the variables is alone in this third system. But this y looks like the easiest thing to get alone because it's the least complicated. So I'm going to choose to subtract 7x from each side in order to accomplish the goal of isolating one of the variables. Now that I have an expression for y, I can substitute that into the other equation where the y would have gone. So I'm going to start rewriting that equation. I'm going to say 2x plus 3, and when I run into where the y would have been, I'm going to substitute this expression that's equal to y. That's then equal to 11. So now we're ready for step 3, solve the single variable equation. Kind of like we did in the first example, we've got to distribute. So we've got plus 30 minus 21x equals 11. Then we can combine our like terms. Negative 19x plus 30 equals 11. We can subtract 30 from each side. So negative 19x equals negative 19. And when we divide both sides by negative 19, we see that x is equal to positive 1. So we're back to step 4, substitute for the second time. So now when I substitute, I'm going to take that x equals 1, and I can go back to this first equation, the original second equation, or even this isolated version of the second equation. And that's where I'm actually going to go because that looks the easiest place to put that x. So when I go in there, I'm going to say that y is equal to 10 minus 7 times 1. Well, 7 times 1 is just 7, and 10 minus 7 is 3. So I can now see that the solution to my system is the 1 that we found for the x and the 3 that we found for the y. So there's my point of intersection.